I am Dr. Basavaraj, Professor, Department of Electronics and Communication Engineering, Siddhartha Institute of Science and Technology, Puttur. So now, today we are going to discuss about the Maxwell's equations. So Maxwell's gave 4 equations for electromagnetic fields. So these 4 equations are very, very important. And Maxwell's is gone through all the electromagnetic equations, and finally he given a conclusion that these 4 equations are very, very important to understand electromagnetic fields and also to derive the wave equations, EM wave equations, and also to analyze the EM wave equations in a wireless media and also in a conductor. So is given the 4 Maxwell's equations. Those Maxwell's equations, we are going to discuss. So the first Maxwell's equations is derived from Gauss law of electricity. So he is not invented these laws, but he has gone through already the laws has been given. So for electric fields, if the charge at rest, then there is a field will be exist around the charge. So then if it is in a closed path, if the charge is enclosed in a closed path, then there is electric fields will be out from the closed path. So Gauss law is given one of the equation that a closed surface integral of electric flux density is always equal to the charge enclosed over that surface. It means that any shape of the closed surface, it consists of a charge particles, and the total electric flux coming out of that closed surface is equal to the net charge enclosed in that closed surface. So that is Gauss law, and same we are going to call as a Maxwell's first equations. Then Maxwell's second equations is also derived from the Gauss law. Gauss law is given for electromagnetic fields. So here the electromagnetic fields are for a closed surface is always equal to 0. The reason is the magnet consists of 2 poles, north and south pole. So if any small piece of magnet, if you take, it is having 2 poles. For a closed loop, the outgoing magnetic fields is equal to incoming magnetic fields. So for a closed loop, for magnetic flux, total net magnetic flux is equal to 0. This is given by Gauss for magnetism. So same we are going to call as a Maxwell's second equation. Then for Maxwell's third equations, it is actually given by Faraday's law of electromagnetic induction. So Faraday is given the this law for electromagnetic induction. What he said is, see, as earlier we have discussed about if there is a current flow through a conductor, then magnetic fields are produced around the conductor. Then Faraday says in other way, that is, if the current can produce a magnetic field, why not magnetic fields can produce a current? So he proved, after conducting many experiments, he come to a conclusion that the magnetic fields can able to produce a current. So he took a closed circuit and he taken another one bar magnet, and he made variations of that bar magnet on the closed circuit. Then he can able to find there is a flow of current in the closed path which is not having any power source. So that is called the Faraday's law of electromagnetic induction. So it says that an electromotive force, that is nothing but a voltage, we are going to call in a circuit theory, that we are going to call as a voltage. So that electromotive force is induced in a closed circuit is equal to the time varying magnetic field. So this given by the Faraday's, so we are going to call it a Faraday law, and this we are going to call it a Maxwell's third equations. Then coming to the Maxwell's fourth equation is derived from the Ampere's law. So what Ampere says is that the magnetic fields are produced by flowing current through a conductor. So how much that magnetic fields, so that is given, that is the total, the magnetic fields produced depend upon the current flowing through, the net current flowing through a conductor. So that is given by Ampere's law. Magnetic field can be either produced by electric current or by the alternating electric field. See, here the Maxwell's, he's gone through the Ampere's law, and he added another one that is called displacement current. See, conducted experiments, usually we know that the current is going to flow for a closed circuit. To flow a current, there should be a closed path should be required. But here, even though there is a gap, the open in the circuit, he could be able to find there is another one current, because as per the Ampere's law, if there is a current flow through a conductor, magnetic fields are produced. So you can able to find in the gap of the circuit, there is a magnetic fields. Then there is a sort of current, but usually as per the circuit law, the current flows only through a closed path. So, but he could able to find the magnetic fields. So there is some sort of similar type of current is going to flow. That is given the another name as displacement current. So is added Ampere's law with an displacement current, that we are going to call as a Maxwell's fourth equations. Now we'll see in the mathematical form these Maxwell's equation, that is del dot D equal to rho, means this del is the nothing but it is a three-dimensional differential operator. So divergence of D means D is nothing but here electric flux density. The electric flux coming out of a closed surface is equal to the charge enclosed in that surface, that is charge density. The charge per volume, that is we are going to call it the charge density. Here the total electric fields coming out from a closed path, that is equal to the charge enclosed in that closed path. Then this del dot B, once again this is a divergence. We are going to call it a del dot B is a divergence of magnetic fields, that is for a closed path, it is equal to 0. That is net magnetic flux coming out, that is equal to coming in. So total net flux equal to 0. Then we are going to call it a curl of E. This del cross E is nothing but a curl of E. Here that is nothing but a EMF. EMF the produced in a circuit, that is equal to the rate of change of magnetic flux density. V is nothing but magnetic flux density. Dou by dou T is nothing but rate of change of magnetic flux density. So negative signs due to Lenz's law. So it is the direction of the current flowing through the other circuit is opposite to the which is cause producing for it. Then curl of H, that is nothing but a magnetic field intensity, that is over a closed path, that is equal to the current density, and there's a displacement current density dou D by dou T. So this is another one as it is given by the Maxwell's. It is he is told that there is another current, that is displacement current due to the magnetic field, alternating magnetic field. The same once again we are represented in differential form as well as in integral form. So the first Maxwell's equation, Gauss law, from the Gauss law, del dot D equal to rho V, that is volume charge density. This means that the divergence of D, divergence of magnetic flux density over a closed path, that is equal to the total charge enclosed in that closed path. So it is also to be represented in integral form, that is integration of over a closed surface d dot ds equal to the integration of volume integration of rho v dou v, that is equal to the total charge enclosed in that closed surface. Then Faraday law, that is EMF del cross E, that is EMF produced, that is equal to rate of change of magnetic flux density. Then similarly, in integral form, E dot dl, that is EMF, we are going to represent in integral form for a closed path, that is equal to integration of rate of change of magnetic flux density dot ds. ds is the here, that is surface area. So Gauss law for magnetics, that is the magnetic net magnetic flux for a closed path, that is equal to 0, divergence of magnetic flux density. Similarly, in integral form, or for a closed surface, the B dot ds is nothing but magnetic flux density for a closed path, that is equal to 0. Then from Ampere circuit law, that is the curl of H is nothing but magnetic intensity, magnetic field intensity over a closed path, that is equal to the current density and the displacement current density. Then for in integral form, similarly in integral form, so H dot dl or a closed path is equal to the surface integral of J dot dou d by dou t dot ds. Okay.